Okay, well, welcome everyone to the TILOS seminar. I'm very happy to introduce Sean Gao, who's an assistant professor of CSE here at UC San Diego. Sean works on search and optimization algorithms for improving the quality of automation and autonomous systems. In TILOS, he bridges chips and foundations, even as much of his work is with robotics folks. And in TILOS, he works on derivative-free optimization, sum of squares proof systems with scaling of design verification as the overarching goal. His work has been recognized many times over, the NSF Career Award, the Air Force Young Investigator Award, the Silver Medal for the Kurt Gödel Prize. And today, without further ado, he will tell us about reasoning numerically. Take it away, Sean.
Okay, thank you, Andrew. Thank you all for being here. And originally, I wanted to delay my TILOS talk till after we have some TILOS specific results, but Andrew convinced me that it's good to give a high-level talk early anyway, so that you all know where I came from and all that, because usually it's hard to explain that, and it's often a long story, and I'll try to tell part of that story today. So let me just start on the ambitious goal of thinking about all of engineering and tech, it's aerospace, biomedical domains, robotics, and computer engineering. We can think of it as one particular instance of one engineering field. And what is, if we think at that level of what is the shared problem for all these different domains, I would say constraint optimization. Okay, which of course is the topic of TILOS. And if we write down things in some mathematical forms, basically we have a state space. We have a space of all the things that we care about, and the space for the designs for the things that we want to engineer, it is a space of functions, right? So this big F is the space of all the things that we can think about engineering. And usually that means we have to define the program language for this, the hardware language for this, or say hypothesis classes if we're thinking about learning-based methods. And then one of the most important thing is in engineering, by default, we need to do things right. Okay, so otherwise we probably wouldn't call it engineering. So when we say doing something right, we usually mean there's a strict list of requirements we need to impose on these functions that we design. Okay, so here I write them as a big formula phi, and this phi can be really complicated. We will have some instances later. And also, of course, if we take the optimization perspective on top of this, basically out of all the possible designs that satisfy the requirements that we have, how do we optimize the performance with some metric of, which will be kind of a functional over the designs that we can come up with. Okay. So overall, all engineering problems are, to me, essentially like this. So you have the space X, and then the space of functions of designs that we can use. And within the space of functions, we have a subset that's determined by the requirements that we have, and we can only basically ideally only take designs or functions from the subset of the space. And then there is some objective functional that evaluates, given whatever design we have, how good or bad we are doing. And if you think of them as a kind of a landscape over the space of designs and the space of inputs for the system, it's something like this, right? So, of course, whenever we write, we show something as a landscape, the most clear part is this kind of z-axis, the j, the performance functional that we think about, and we think about it as a very complex landscape. But I want to point out that this phi that I'm showing, do you see the this phi that's actually in the function space it's quite often more important even than the performance metric. Basically, you first make sure that you can satisfy what you are supposed to do, and then within that subset, you maximize the J. And to me, the whole practice or processes of engineering is about moving in this space. Okay, so you have this landscape, and we sometimes can know what is good, what is bad, and how do we take this problem and try to find some function in the function space of F in the design space, such that we can optimize the objective as much as possible. By the way, feel free to ask questions anytime. I try to stay at a high level, but also being a little bit technical, which means I can't go to much of the details of the technical part. So there can be many places where I seem to be just throwing in formulas from nowhere. Then feel free to stop me. I had quite a few slides on examples, but I was a little bit impatient because I was also grading this couple of days, and I wasn't in my most patient mood. So I deleted some of the examples, but hopefully we'll see. But again, feel free to stop me anytime. So one thing that started my work in this space, thinking about engineering problems in general, was actually the observation that if we think about computer engineering, software, hardware, we have been quite successful in this particular domain. Of course, we are successful in many engineering domains, but the design of hardware and software, I feel, is very different from many of the other, say, mechanical systems. And here I'm showing, hardware. Of course, we know, all these hardware designs are extremely hard. There are huge industries on these, and a lot of efforts and all the tools and infrastructure built on, just for this. And on the right-hand side, I'm trying to have this very old-fashioned way of kind of showing the complexity of the software. I saw this picture from some very old talk, and basically saying, if you take any piece of software that we use on a daily basis, operating system, compilers, web browsers, and if you print out the code, the software code, and stack all the papers of the printouts, you will easily have a stack that's taller than any of the huge buildings that we have. And of course, I don't need to convince you about this anymore. It used to be an argument that people say. And basically, if we think about the things that we can engineer in the domain of, let's say, the digital systems, okay, hardware, software, the functions that we can come up with are kind of orders of magnitude more complex than many of the other domains. And also, whenever you want an engineering system to do, an engineered system to do something that's sophisticated, you would have to rely on the digital parts, okay? And one thing that I don't know if everyone knows is that, the software part in software, hardware, chips part of modern cars and airplanes are over 70% of their total cost. Maybe that's already an underestimation. And of course, if we all these digital parts are everywhere, and we talk about Internet of Things, smart cities, and all that. Basically, we've been pretty successful. So of course, I came from this full methods community, and we keep saying, okay, there are many bad things happening in the design process of software and hardware, but still, I think if we take a high level positive perspective, we have been doing pretty well. And the most interesting part of digital design is, say, compared to a non-digital mechanical system, that there are many complicated systems like that. But one difference, one major difference is When you write a piece of code, okay, when you have a design of a circuit, of a software, after you write those things down, you don't directly know what it's going to do. Okay, so as long as the thing gets longer than tens of lines of code, it becomes extremely hard to actually understand it, right? And this is quite different from, say, putting physical parts together, and we can have often intuition about what they're going to do. So digital systems are built, in this way, and this whole process is completely mathematical. So tools that facilitate mathematical reasoning of the behaviors have been crucial in the success of the digital systems. Okay, so these engineered systems are all there doing so many things, and their success really depends on the methods and tools that we have developed for the engineering, for the rigorous engineering of them. And just for a few small examples on that, if we think about hardware design, right, and we try to say come up with a circuit that can do multiplication, right? And if we think about this overall design problem of having a state space, having a function space, so basically the design space, the function space that we're dealing with here is all the Verilog programs. So first, I'm staying at the level of Verilog, and there are a lot of lower level stacks, routing placement, and all that, and staying at the Verilog level. And then the requirements we have when we come up with a program like this, a design like this, the requirements would be for, say, this circuit, we will always make sure that the output of this circuit, of this program, is the product of the multiplication of these two inputs, right? So for any x, y in the range of values that we care about, it's always correct. And on top of that, assuming that the circuit can always do it correctly, we have performance metrics about, improving the efficiency, energy, or minimizing the size of this circuit. And if you think about software systems, it's the same overall task of engineering, right? So the design space is now, I wouldn't say it's larger, but it's a bit more complex, same size as the Verilog program space. You probably try to implement, for instance, a compiler, an interpreter from some language to some other language, or to assembly code. The design space would be all of the programs that you can write down in the language that you're given, right? And then the requirements, say, for a compiler, the requirements would be for any input program that you give to this compiler, the semantics is preserved, from P to the output of applying this compiler to this P, right? So in the formula that I write here, basically, if you think about the output of the compiler and interpret that over the C programs, because here I'm saying, we're interpreting from Python to C programs. The semantics over C has to be exactly the same as the semantics of the original, say, Python program, right? That's my overall requirement. That's the fee in the function space that I need to care about. And then on top of that, if I care about performance, I would try to optimize the compiler so that the output of the compiled code is efficient and memory efficient and time efficient, and for important classes of input programs. Okay. So if we see these instances as particular tasks of engineering, then what we have in the design or implementation of digital systems is this whole stack of infrastructure with mathematical rigor that allows us to do these very well. Okay, so we have program languages with formal semantics. We have these languages that create all these levels of abstractions. On the corner, I show this all the levels in hardware design that we need to worry about, which are facilitated by all the different levels of languages that we have. And the rigor of all these designs are already built into these interface of programming or design. Okay, And on top of that, we have this area of formal methods that try to really enforce the properties that we need, the feed that we have on top of these designs. For that, we can use formal languages, which usually some kind of logic, some mathematically rigorous way of describing what we want. In the simplest case, it's like, it's multiplication. But, what if you want to express the properties of an operating system, right? Or a web browser, and all those need really elaborate formal languages to define. And also we have these automation tools, right? So automated reasoning tools that allow us to actually take a piece of design or engineered function and then either be able to say that it really guarantees the requirements that we impose, or find bugs that falsifies the design, which would be used in the future rounds of engineering. And again, if we think about the examples we just talked about, if you have a piece of code, Verilog code that defines a circuit, say multiplying two things, what we can do is we can encode the whole process of this function, right? So we can go through the function, which is now a program. We can go through it line by line. And for each line, we can define a small propositional logic formula that takes you from the previous state of the input to the next state that's transformed by the program. And we do that for the whole thing, and then we collect one big formula phi here, which is the interpretation of these design F that we have, that defines a relation between my input x1, x2, and the output y, right? And we want to say this, it can be routinely done so that this phi formula expresses exactly what you implement in this Verilog program, okay? And then we take that and use an automated reasoning tool and say, and pose the query of, does there exist any input, x1, x2, such that if I do things according to the propositional logic formula that defines my design, the output is always exactly the product of the inputs. Okay, so this whole query can be written down precisely as a propositional logic formula, which we call a SAT problem. And usually these problems are big. I mean, even for this multiplication, you see the Verilog program is maybe a few hundred lines, and then this formula itself is pretty big. But we have these automated reasoning tools called SAT solvers, and they can just take the query, which can be a big formula, and tell us whether there are any inputs that can falsify the property that we actually need. Okay, so the query we give to these automated reasoning tools are always about, can you find me what we call a counterexample to the overall property that I need for the design that I came up with? And if the solver says your query is unsatisfiable, which means I cannot find any inputs that falsifies this equivalence between the circuit and the multiplication, then I can say, the whole design is correct. This whole function F is in the big phi set of my function space. Or if I am able to find any satisfying solution to this, which means you can find concrete inputs that falsifies the overall property, then the design is falsified, but the concrete counterexamples can be used for improving the design. You can repair it, you can debug it. And the core part of this is SAT solvers. Okay, SAT solvers, of course, it tries to solve this fundamental and incomplete problem of Boolean satisfiability. And the development started in maybe the 60s, and by early 2000s, we have these really good SAT solvers as the core automated reasoning tools for hardware designs. And it's still surprising to this day that they can often handle, tens of thousands of variables, because if you think about the whole state space of that, it's crazy. If you think about the typical exponential blow up argument, and still there's no good theory explaining why sometimes they work, sometimes sometimes they don't work, of course, because it's NP complete. And that is, coming out with a good theory about when they work is still a challenging open problem that I hope in TILOS we can make some progress towards it. And the core of these SAS solvers is a kind of smart backtracking search algorithm. Okay, so basically, the space, of course, is exponential, and at a high level, we're just trying to span an exponential tree over this whole space. But the search in this tree can be very smart in the sense that, of course, we try to, we try different solutions, and then when solutions don't work out, we go back to flip some decisions and try other possibilities. But during this process, there is what people call conflict-driven, cross-learning-based way of doing the backtracking, so that based on local inconsistencies or local conflicts of the search, you go in part of the space and realize there are no solutions. You can actually learn an explanation for why things don't work out, and add those explanations as part of your whole requirements, so that in the future you can prevent the big subsets of the search space that you have already seen. And with that mechanism, actually, you can scale a lot on very complicated constraint sets. And one thing I want to emphasize is that, sometimes when people hear about formal method, people just say, okay, verification, with the idea of you just design the whole thing and throw it to a SAS solver, and it will just tell you good or bad and give you an answer. But that's almost never the actual thing that people do, because although these solvers are good and they can handle a lot of variables, they can handle reasonably big problems, but for any practical design, anything that's more complicated than this multiplier that I just mentioned, you need formal reasoning and automated tools in all levels of the design, so that you break down things to small parts, so that each small part you can probably use a reasoning tool to deal with, and overall the whole quality still relies on a full stack design automation. And then if we think about software, right? In hardware we're doing great, software we're doing pretty well as well. How do you say that a compiler is always correct? Again, the property that we ask for is very strong. It says for any possible programs, okay, your state space is the X is actually all the programs that you can think about. You need this function, this compiler function, to always give you the right thing that's equivalent semantically to what you took as input. Right, and that is a very hard claim to make. So what people need to do is to actually have good programming languages that kind of integrate some level of formal reasoning already. And if you think mathematically, for things like compilers, the best candidate for writing them is functional programming languages, in which you can actually have the correspondence between the program you write and the mathematical proofs of their correctness for free, basically, if you write in that language. And in general, we need to make inductive proofs to make claims about these very complicated functions. And also the automated reasoning tools, which we call SMT solvers. The SMT is an extension of SAS solvers, and the full name is satisfiability modulo theories, because if you think about software programs, you need to think about strings, you need to think about integers and other things, and they correspond to different theories of the logic formulas. So that's why SMT is the generalization of SAT. And for software, which is this much bigger design space, the only hope is this kind of induction-based proof techniques, right? So there has been significant progress in the system software stacks, operating systems, compilers, with very elaborate process of doing rigorous engineering to come up with things that really satisfy the requirements that we need, about compilers, about operating systems, and all that. And one type of tool called interactive theorem provers are the foundational frameworks for this type of rigorous engineering. And the programming languages need to produce the rigorous hierarchical abstractions that are important for establishing this. Of course, I don't want to focus on too much about software programs, which there's this whole community of program languages, software engineering doing a lot of work in this specific form of engineering. But the general perspective that we can transfer from software programs to, say, other engineering domains is that, digital systems, either hardware or software, if we think about them as, these functions that are applied to the input space or the state space of the system, they define discrete dynamical systems over time, right? And things that we can possibly ask for these systems, there's a theorem basically saying, you can always decompose any requirements you have about discrete dynamical systems into two types of things, two types of requirement. One is you want bad things never happen, right? You never want any input that doesn't give you the right value as the output, either compilers or multipliers and anything like that. You don't want bad things to happen. And also, if we think about recursion, we think about loops, we need to say the good things eventually happen. Okay, so there are these two dual notions of requirements that we have. And skipping over a lot of technical details, the general methods for establishing these requirements are always some form of, in software engineering, we call it inductive invariance. And in general, we can say a value-based system. So the idea is, the function that you design defines a particular movement in the space of X, right? And it generates your sequence of states, X0, X1, X2. And then the properties that we want to impose are always about, okay, is this sequence going to converge to something? Is this sequence going to take values that we never want them to take, right? And the ways to proving them or to rigorously engineer the function to satisfy them is always by looking for a landscape of values that I can use as a metric for determining whether my states are converging or whether they're always safe. So if we write them down logically, basically we're looking for a V function, which is the function going from the states to some values, so that, for instance, if you want to say something is safe, you basically create a landscape that covers all the states that you have, and also make sure that all the states that you can take are disjoint from the unsafe properties that you have. And the kind of inductive invariant way of doing that is to find a value function V, such that if you're currently, if you're X, I don't know if you see my cursor here, if you are currently in this safe space, and then you take one transition with under this function that you designed, and then you still stay within the safe space. Okay, and then liveness properties, which are good things eventually happen. Similar, you create a landscape that says, if I ever take a step under my F going from X to X prime, sorry, there's a typo, it should be X, then the value decreases in some sense, okay? And this is the general way of establishing, say, any convergence property or any safety properties, So in control, we would have Lyapunov functions doing exactly the same thing. In stochastic systems, it would have martingales, super martingales to do this. Essentially, all that we try to do in again, I'm skipping over the details here, but usually the process of rigorous engineering is about translating this overall problem of maximizing the performance subject to some constraint into this form of search of both the design program models, this F, and the search for a certificate or a value landscape, such that for all possible inputs in my state space, I can guarantee certain requirements or constraints. Okay, so overall, if I really try to express all these challenging design problems, they're almost always of this form. And for, again, digital systems, we have developed tools for doing this. So the functions F, or what we can write down in programming interfaces, and the process of coming up with certificates or value landscapes can be done, at least partially automatically by automated reasoning tools and proof assistant. And then in the end, we need to certify these overall claim that for all possible inputs, the requirements about these nice properties actually hold. So these are things that we actually write down in formal ways in different logics, right? And then, this is where I started thinking about beyond digital systems and think about, because all of the different engineering tasks, all of different challenges, essentially in the end, they boil down to solving this kind of problems. Of course, we don't always have the right logic for expressing, all these different tasks, but essentially they're all trying to solve the same core computational problem. For instance, I already mentioned lambda functions. If you take a big robotic system and you try to say it's stable, okay, then the engineering process of coming up with our argument or the control and the controller to make it stable is exactly of this form. Later, we're going to make that more precise. And whenever you fail to do that, you have this. Okay, so whenever this logic formula is not true, if you really put that function into practical use, this is of course one of the rocket that SpaceX used, in their experiments. And whenever you see things going wrong, it's always because you can't, really solve this problem. So this concept of thinking about, the action of engineered functions over state spaces, this perspective goes, is shared between discrete systems and continuous systems. So software system, hardware system, we think about things over discrete time. But, for dynamical systems, it's exactly the same thing. Just, whenever we take a step, now we need to think about the derivative over time. We need to think about the lead derivative of the value functions. And to be precise, the methods of Lambda control for nonlinear systems, it's exactly trying to construct basically an energy, which is a metric over a landscape, over the state space, so that you can argue that the system is stable because it's always decreasing in that energy level. Again, energy level is just this value landscape that you create. Okay? Just intuitively, if you argue that a ball is going to stay at the bottom of the bowl, that's the Laplace argument that you are constructing. So there is actually a lot of hope of taking what we do pretty well in hardware and software systems and do them in other domains. So in control, if I take exactly the same type of queries, I can think about F as the control design that I have. It's probably the whole system. And then the V in this specific stability case will be the Laplace functions that I try to come up with. And then over the whole state space, I have to satisfy the Laplace conditions, which are basically those inductive proofs that I will be able to write down. But the challenge is existing full methods reasoning tools, they can never do this, okay? Existing tools are really scared. They're really successful over digital things, but really scared of real numbers and continuous functions. And this limitation is very fundamental because, with logics, we deal with discrete stuff and, we take inputs that are finite size. But real numbers, if you really think about it, the mathematics, they're really functions over integers. So they're really infinite strings, okay? And there's this hope of thinking about these type of control problems in this logical way. But once you see the dynamical system, the equations that you actually need, the functions that you actually need to write down the system so that they become part of your overall requirement fee, there used to be no hope from automated reasoning tools because these are things that we can't have a good logic for. So that's where my research actually started. And so I feel it's just weird that, on the one hand, we do have some systems working well, right? And on the other hand, if we do a kind of formal, rigorous, symbolic approach, we can never say anything about them. So, so we started thinking, how about we just be crazy first and think about this language that can incorporate anything you need in engineering. Okay, what that means is, we need a very rich logic that allows us to use all these nonlinear functions, polynomials, trigonometric functions, exponential logs, and all the ODs and PDs and all that. And whenever something is useful for practical engineering, we should think about them in this logic. And this is, of course, extremely expressive, just like how, propositional logic, even though it looks simple, it can express everything you can possibly need about digital systems, right? If you allow the use of all these continuous functions, you can actually express almost all engineering problems in this language. But at the same time, like we said, it's extremely undecidable. It just, you take it and you can write down things that express, fancy engineering tasks, but you can never hope to get automated procedures to deal with these formulas. At least, it used to be that case. Just to show you the expressiveness of whenever you have these functions, what you can do with them, what are the problems that you can write down with them. Let me show you this. Okay, so if I ever want to buy an autonomous car, I will want something that can do this instead of driving like me, because what's the point of having that? So, and if we really think about this problem, if we really take this seriously, okay, it's something that you can actually write down in this logic. So first of all, what are the movements here? It's just you start somewhere and then you take a turn and then go into a different drifting dynamics, right? So if we describe it in kind of a computational way, really you have some starting point and then you first follow some dynamics. It would be a set of differential equations that kind of accelerates the car. And then at some point you make a decision of turning, right? You do something. And then you enter this different continuous physics part of drifting the car. And then at some point you're parked and you stop the whole process, right? And this will be something that you can easily write down in the logic that I just proposed. Okay, so it's nothing but going from x0 and you go follow the dynamics of acceleration, going from time 0 to t0, and you get a new state. And then at that state, you do something about turning, and then you follow a different set of differential equations, and then you stop. Okay. So if you allow all these different functions in all these different numerical functions in the language, you can actually write this down. And if you also have a solver to do this, you can actually come up with the precise values of when you should turn, when you should start, when you should park, and actually, use it in the car. Of course, a lot of other things will have to go on, but mathematically, that's essentially the complexity of the problem. Okay, so recognizing how useful this logic would be, we started thinking about, okay, in the traditional way of thinking, you can't do anything about this very expressive logic. But what if we redefine reasoning in the first place? Okay, we want to do automated reasoning, but maybe that's something different over continuous space, over numerical things than what we used to think about in the digital space. And then it turned out that we only need to make a tiny tweak in the definition of the reasoning problem, which incorporates this natural notion of numerical errors that we have everywhere in any kind of real world engineering, right? And logically, all we need is to kind of change the yes or no semantics of logic formulas with something that can tolerate one-sided numerical perturbations. Okay, so we can always ask, instead of asking whether a formula is true or false, asking for a solution for that, we can instead ask for whether it's false or what we call delta true. And this delta true is just something that can be easily defined as a syntactic perturbation or a syntactic weakening of the original formula that kind of weakens my problem on one side. And I don't want to give the whole logical definitions of all these, but just to show you the simple a simple example of this intuition, which is if you take an arbitrarily nonlinear function f, right, and we all know the zero crossing problem is extremely hard, right? Which is, okay, finding values to solve this equation to make this function exactly zero. But if you allow any numerical bound, say I only need the absolute value of f to be within delta, right? Delta will be a positive number. It will become much easier, okay, intuitively and also computationally. And so we came up with this theory about basically, reasoning numerically, changing the definition of reasoning so that we can actually hope to do it with nonlinear functions and in continuous spaces. So we defined this delta descent problem for all of that rich logic where you will allow any, all these PDs in the functions. And once you define this different form of reasoning, the whole thing becomes decidable. Okay, so basically it is possible to actually take the formula I just wrote about this drift and park thing, and in principle ask an automated reasoning tool to solve it, to actually find the values that actually satisfy the formula. Okay, in principle. Of course, there's always the challenge of a huge space and the complexity of the computation. But at the same time, more surprisingly, so this was, we realized this after making the proof about decidability. We say, what about complexity? And realize that actually it puts the continuous stuff at exactly the same level as the digital stuff. The precise statement I didn't write on slide is basically, if you take any sigma n formula in this logic, the complexity would be, sigma np to the raised up to the complexity of the numerical functions. But anyway, as a small example, the drift and park formula actually is only in NP. It's it's basically exactly the same class as what your SAS solvers can deal with. Okay, and that applies to all these other, exist for all formulas that I talked about. And the core theoretical message here is the challenges of design problems over discrete spaces where we have been pretty successful, and the continuous spaces where the traditional kind of successful rigorous engineering methods don't apply easily. But really, if you think about them computationally, they're really equivalent from a complexity perspective. So from there, we started developing this automated reasoning tool, DReal, and we use a search-based, backtracking search with CDCL type of approach over the continuous domains. Okay, so we basically take the continuous domain and think about this analogy between the continuous and the discrete, and we try to see how much the backtracking search algorithm can take us. And within this backtracking search, we need to do numerical procedures everywhere to just ground the reasoning in the continuous spaces. So the solver has been used in a bunch of different engineering domains and with some small successes. And one thing that I really want to emphasize is, if you take this example of coming up with really stable controllers, using automated reasoning tools actually allows us to go beyond, much beyond what what people have typically been doing in this domain. So, if you think about this overall problem of coming up with a Lyapunov function, we can actually use neural networks, just because now we can be very general and think about all these nonlinear functions. So why not neural networks? And the landscape that we're looking for can just be a generic neural network, which we can train with samples of the space, and then we impose the requirement such that in the end this whole formula can be fully guaranteed by the automated reasoning tool. Okay, so, and with that, we can actually come up with a precise statement. So this red circle is sort of the place where this overall requirement phi is guaranteed to be true. And that corresponds to the region of space where your system is guaranteed to be stable. And by doing this automated reasoning tool approach, we can find Lyapunov functions that are way beyond what people, way beyond the hypothesis class that people usually have, because you can have generic nonlinear approximators, neural networks to do this. And at the same time, you can have complete claims about the stable regions. And, in principle, if you can find these Lyapunov functions and stability regions, you wouldn't see that SpaceX rocket exploding. But of course, there's a lot of gap as well. But at least mathematically, the use of these automated reasoning tools over continuous domains give us the ability of dealing with really nonlinear functions, really non-convex landscapes, and kind of use this brute force way of backtracking search of getting what we want. Okay, and that we feel has to be a important piece if we think about rigorous engineering in general, over continuous spaces. And now that we keep talking about neural network controllers, neural network this, neural networks that, eventually, if you really want to put them in practice, you have to have these tools that makes us comfortable with engineering these functions. And what we mean by being comfortable with using and engineering those functions is really about solving these questions that we can pose as automated reasoning problems. Those are specific things that we did. And I think there is really this opportunity of taking what we have been pretty successful about from the digital world to the more general engineering, real world engineering domains. But of course, all that we have been doing is to have some, academic tools and small examples to show that there are values in these tools. But of course, the whole space is huge, and we need all the things we have been developing for the digital systems in, the overall engineering problems as well. In particular, the infrastructure for hierarchical abstraction, if you think about, how people manufacture cars, how people manufacture airplanes and nuclear plants, biomedical stuff, that hierarchical abstraction infrastructure is just not there. Okay, and that is something that will probably take a very long time to solve. And of course, with the help of better and better computational tools and more and more automation, this will be become easier and easier. For instance, Python is getting adopted everywhere, and a lot of the designs in many different spaces, you can actually see them as just Python programs, and from there, many things become possible. And but I want to emphasize that we have this DReal tool that implements something that we think makes sense, but still it's still very naive. So we're doing backtracking search with numerical procedures embedded in them. But really, after bridging the gap between the discrete and the continuous and the kind of symbolic and the numerical, we can see that the core problems that we talk about in, about rigorous engineering for these digital systems, we think about their continuous versions, they're everywhere defining the hard problems in almost all areas, right? So really, exists for all is just a logical way of talking about min-max problems, right? And if we think about that, of course, robust optimization, game theory, EM algorithms, generative adversarial networks, all the clever things that people have been developing in all these different contexts, they're really different approaches to solving these core challenging computational problems. And going forward, I really hope that we can start thinking about how to merge and unify all these different styles of moving in this crazy space of designs with highly non-convex landscapes. How do we mix all these strategies together? And each subfield of, let's say, if we think about the whole field as moving in the landscape, each subfield of the different approaches, numerical optimization really focuses on, okay, you start from some point, you think about the geometric properties of the space around you, right? And you try to make the best move based on that. And because that's sort of the core mechanisms you have, there's a lot of effort into formulating the landscape so that you can make these algorithms work well, right? And then, which of course is convex optimization and how to turn things into things that you can reasonably solve. And then backtracking search is coming from a different direction, saying, okay, you can give me a crazily nonlinear function, and I can just go into the space and start forming my, exponentially sized search tree over the whole space and try to do it in a smart way, right? And many of the approaches utilize symbolic and algebraic information about what the function is, what the particular constraints you have, and all that, right? And then, of course, there's, sampling-based methods, particle-based methods that try to kind of adapt the distribution of your samples to the underlying landscape just so that you can come up with the optimal solutions. And I really hope we can start thinking about the overall algorithmic framework that ideally puts all these different approaches in their right places. Can we, use more symbolic and algebraic and constraint-based methods to think about how to decompose the space into kind of simple pieces? By the way, this graph comes from what we call cylindrical algebraic decomposition, which is when you have highly nonlinear polynomials, there are ways to actually decompose the space and try to have simple pieces to do your search. And then numerical and geometric approaches would allow us to move in the best possible way, in these local neighborhoods where, ideally the overall combinatorial approach puts you in. And then sampling-based and particle-based methods allow us to actually query the landscape and heuristically guide this global search that can benefit both the algebraic and the analytic approaches. So yeah, time is about over. Again, overall, I hope I hope you are coming. I don't know. I mean, I try to formulate all these different types of engineering problems in this overall same mathematical abstract definition, and really the hard problems across all of engineering domains are computationally equivalent, and we can make very precise statements about that. And the formal reasoning tools and infrastructures for building good hardware software systems in the digital domain can be considered a good, promising, a good role model, a good role model for the other domains as well. And we should formulate what we need precisely and have the tools to help us engineering the whole thing in a rigorous way. But at the same time, there are a lot that needs to be done to unify all these different perspectives, approaches, and insights from roughly the same problem across all different contexts. And, just so that we can tackle the shared challenge. Yeah, that's sort of my conclusion slide. And I added this slide just 5 minutes before the talk. So computers were really invented 100 years ago to kind of about this dream of automating all the mathematics, right? So people are saying, can we? Well, is mathematics? Cannot mathematics be automated? And of course, in the end, everyone knows it cannot be. Okay, but still, the whole industry of computer science started from that. And I keep wondering, is it probably the time for us to actually think about the same type of questions for engineering as well? And TILOS may just be a great opportunity to do some of the initial work in that as well. And with that, I guess I will that's it. This music is probably disturbing.
Okay, so thanks. Thanks, Sean. For the really interesting talk. I see that Andrew is gone. So I don't know, Aria, you want to take the Q&A, or do you want me to do that? Let's first give Sean a round of applause for the very interesting talk.
Thanks.
Yeah, it was a great talk, Sean. I see that a few hands are up. For example, Sean Joy's hand is up if you have a question.
Yeah, hi, that was a great talk. Thanks, Sicun. One question I had is, in moving back and forth between these discrete and continuous domains, in your, for the kinds of problems and the kind of scenarios you have in mind, which seem really very broad, how much of an issue is precision? Like, should we be worrying about it? Should we be using models of computation in which infinite precision computations are possible? Like, how much of an issue is that?
Yeah, so basically, this framework of delta decisions for formulas with nonlinear real functions allows us to explicitly take numerical errors into account. So basically, if delta is any positive real number, then this whole thing is decidable, but the complexity is exponential in delta, of course. And if we have to have infinite precisions, then we lose the promise of computability. So basically, if delta is 0, we go back to the standard decision problem of then none of this becomes computable. So so this delta definition is a simplistic one, and there are a lot of refinements that can be done over it. But roughly, I think basically whenever in practice we can have a notion of tolerable error, as long as we can quantify that, then we can talk about complexity. We can make claims about what problems are hard at what level. And then if we have to vary about infinite precision, which for, if we want to do mathematical proofs for many, say, geometric theorems, we have to do that. Then this type of reasoning tools with numerical procedures as part of them will just not work. We will have to do, symbolic reasoning to do with algebraic stuff. Yeah.
Okay, cool. Thanks.
Young, there is another hand.
Yes, so I have a question about the neural function part. So in the presentation, you present some results on training neural network to certify some proper dynamic systems. So I'm wondering how do you guarantee the neural network satisfy the upper function requirement? So do you design the structure of the neural network, or just training the weight of the neural network to satisfy the requirement? Can you say a little bit more about that?
Yeah, so that's exactly where we need automated reasoning tool. So what you have to do is you take this whole neural network as the lambda function, and then you formulate all the requirements you have, which goes into the fee that we wrote there. And then we need the tool to tell us over the entire space of inputs, this whole function satisfies the lambda conditions. So basically, the reasoning tool will just say, yes, this is indeed the case, and then you are done with the design. Or it says for some specific inputs, the lambda conditions are violated. So this part is basically the hard part of global optimization that the reasoning tool is actually used for. And then and this changes things a lot from the conventional way of saying, you first come out with a positive definite lambda function, and then you guarantee the conditions with convex optimization. Yeah, so this makes it quite different, and you have to use reasoning tools to do this.
Okay, thanks.
Is there any other question? Yeah, that was a great talk, Sean. Like I do have some, I think, like some more generic questions. So I think a lot of tools have been developed for to handle constraints that are like either symbolic or numerical, but something like a parity constraint.
Yeah.
Is this like, are there tools to handle those?
Yeah. Okay. By handling, they can always be taken as input queries, right? So, parity constraints, XORs, and all that are known to be one hard classes of queries for, say, SAS solvers and for ILP in general as well. And so yeah, we'll just have to design better algorithm that scales better on those particular classes of queries. There has been some progress in scaling more on those, but yeah, a lot still needs to be done.
Okay, I should get some pointers from you.
Sure, anytime.
Yeah. Okay, thank you. It was a very nice talk. Yeah, let's thank Sean again, and we'll see you next month.
Yep.
Thank you, Sean. Thank you, Greg. Thank you.
Thank you.